The angle of attack. When two reactive ends of a molecule, your X and your Y fragment, come together, they can approach each other from particular trajectories that will be more favorable, and that's what we call the angle of attack. So, for example, when you are attacking an sp3 carbon or an sp3 atom, that typically involves an attack of the incoming group with respect to the group that has the Y atom, the Y group, the leaving group. So the angle of attack is roughly 180 degrees. So here you have an example, your X group attacking this carbon, the Y group leaving, and the attack needs to be on the opposite side. The X needs to attack on the opposite side where the Y, the leaving group, is placed. So that gives you an angle of attack of 180 degrees, give or take. When you're attacking an sp2 carbon or an sp2 atom, for example, a carbon-carbon double bond, a trig attack, then you have to think of that is a planar structure. So you have a carbonyl group, if you have an amine, if you have an alkene, you have that planar structure at 100, the bond angles are 120 degrees. However, you're moving from an sp2 atom to an sp3 atom, which has bond angles, a tetrahedral structure with bond angles of around 109, which is a tetrahedral angles. So the best trajectory for that transformation to happen is if the atom attacking, your X in this case, attacks at an angle of about 109. So this is what this example is trying to show you. You're attacking a planar structure from a roughly 109 degrees, and you end up with that tetrahedral structure with angles roughly 109, which would be the angles for a perfect tetrahedron. sp atoms, for example, an alkyne have a linear, or a nitrile group, have a linear geometry. So you have a bond angle of 180 degrees. And when the reaction takes place, you convert your sp atom into an sp2 atom, which will have a 120 degree bond angle. So the incoming atom needs to approach from an angle of 120 degrees for the cycle to form. And that's the best angle of attack for the reaction to take place. The length of the tether also plays a role. So for example, if you have here ABC atoms, ABC atoms that can attack that triple bond, probably C and B attacks will be easier because the length of the tether is slightly longer and makes that achieving that angle of attack easier than, for example, if the atom that attacks is the one in the position labeled as A. In general, for the attacks of SP, it is reasonably easy to achieve that angle of attack, even with very short tethers. So putting all these things together, Baldwin came up with this suggesting of what suggested trajectories and what size of rings are more likely to form, and whether the ring will be an endo or an exo ring. And that is basically the red crosses mean those are not favorable modes of cyclization. The green means those are more favored cycles, and then there are the ones that there are no prediction using Baldwin's rules. It's important that you think that when a process is disfavored, that doesn't mean that it's impossible. Again, although they are called Baldwin's rules, it would be more appropriate to say that they are guidelines. They just suggest what are the most likely rings to form, the most favored reactions. The ones that, because of the angle of attack and the structure of the size of the tether, will make faster cyclization reactions. A disfavored process can still take place if there are no competing reactions. It's just that because it's a slower process, if there's any competing reaction that could be an inter or intramolecular reaction, it will not proceed, just because those faster reactions will take place instead. But that doesn't mean that they cannot form, those rings cannot form, and there are plenty of rings that are formed that contradict Baldwin's rules. This is, for example, is an example of a formation of two possible rings over this, in this area of the molecule. So you've got the 5-exotrig product and the 6-exotrig product, and they both form, but the most favored one is the one corresponding to the 5-exotrig product in a ratio of 18:1. Baldwin adapted its rules for aldol cyclization. And basically the exo and endo and the tet, trig, and dig parts are the same, but he came up with two different parameters, enol-endo and enol-exo. Enol-endo is a process in which the both carbons of the enolate fragment, the carbon-carbon double bond, the enol group, are incorporated into the ring that has been formed. And enol-exo is when only one of the carbons of that carbon-carbon double bond is incorporated into the ring. So, for example, in the transformation from 183 to 184 that you've got here, we've got an exo attack. The electron flow is outside the ring. Tet because it's an sp3 carbon, and enol-endo because the enol, both carbons of the enol group end up as part of the ring. If you look at this example, again, it's a tet attack because the attack is over an sp3 atom. Exo, again, because the electron flow is outside the cycle that is being formed. But in this case, it's an enol-exo ring formation reaction because only one of the carbons of the enol group is incorporated into the final ring form. So I'm going to ask you to stop the video and have a go at identifying this particular reaction using Baldwin's nomenclature. So if we look first at the atom being attacked, it's an sp2 carbon, so this is a trig attack. If we look at the electron flow, this is an exo attack because the electron flow, the electrons end up outside the ring being formed. And enol-endo or enol-exo, well, in this case, both carbons of the enol fragment, enol functional group, end up in the ring, so this would be an enol-endo reaction. So enol-endo exotrig ring formation. And in a similar fashion, please stop the video now and have a go and identify this particular reaction. So again, this is an sp2 atom, so this is a trig reaction. The electron flow is outside the ring being formed, so it's an exo reaction. And enol-endo or enol-exo, well, in this case, only one of the carbons of the enol group participates in the final ring, so it would be an enol-exo ring formation. And Baldwin's rules for all those cyclizations, well, this is an example of the ones that are favored and the ones that are disfavored. Again, they are guidelines more than rules. Being disfavored doesn't mean that the reactions do not happen. It just means that if there are competing reactions that are faster, those will happen preferentially, and the ring cyclization, the ring formation will not take place. So for example, here is an example of a compound with 3 carbonyl groups in which the 6-enolendo exotrik product of reaction is favored and forms, and the 5-enolendo exotrik is not formed, even if in theory it would be possible, because this is a more favored reaction and will happen faster, so it will happen preferentially to the extent that the other ring forming reaction will not happen. So this is all. This is the end of the series of videos dedicated to stereochemistry and introduction to ring formation. I hope they were useful. If you have any questions, please drop me an email. And thank you very much for watching.